We are in Rosen chapter 3.2 on the growth of functions. And in this chapter, we'll cover these topics. In this video, we'll zoom in on big O notation. I'll just pause to mention one of the mathematicians you see on this slide, Donald Knuth, still living. He was awarded the Turing Prize back in the 1970s. And he is well known in the computer science world for his opus, The Art of Computer Programming. So if you haven't heard of it, I recommend checking it out. I'll let you read about these other mathematicians on your own. All right, this chapter is on the growth of functions, and what do we mean by that? Why do we care about how fast a function grows? Well, we do so in computer science because we solve problems in the small and then we encounter them in the large. As you might probably have done on your own, whenever you write an algorithm and you test it on a small practice problem or example problem, but then you want to apply it to a very large real world problem and you want to know how does the performance change as the size of my problem grows or the size of the input grows. And by understanding that, then you can compare algorithms that purport to solve the same problem. Which one's better? Which one's faster? And indeed, which one is even practical? Because some problems can overwhelm some algorithms. And we'll study this analysis in chapter 3.3 using the theory that we're going to learn in this section. If you'll take later courses, we'll study the growth of functions in more complicated type of algorithms. These are covered in chapter 4 and chapter 8 in Math 350. All right, big O notation. Many of you have probably heard of it. You might have some ideas on what it means. Let's dig into the definition. All right, so if I have two real valued functions, f and g, then I say that f of x is big O of g of x when there are constants c and k such that the absolute value of f of x is less than or equal to c times the absolute value of g of x whenever x is greater than k. So there's c mentioned earlier, and k is the lower bound of x. And the way we read this is f of x is big O of g of x. And as we'll see, it means that g asymptotically dominates f. Big O of g of x is actually a set of functions that satisfy the definition. So you could say that f of x is in big O of g of x. These constants, c and k, are called witnesses to the relationship that f of x is big O of g of x. And the way this generally works is we will pick one and solve for the other. Usually we will pick k and solve for c when we want to show that f of x is big O of g of x. You only need one pair, and it doesn't matter which pair they are, to show that the relationship is true. And we'll also show later how to show that the relationship is not true. All right, here's an illustration. Here is, we say that f of x is big O of g of x. It doesn't mean that f of x is always greater than g of x. It just means that after some value, k, f of x is dominated by a constant times g of x. All right. Once we find a pair of witnesses, we'll know that there's really infinitely many pairs because you can always make k or c larger and still meet the definition of big O. That's what this next line says. Um, Sometimes you might encounter the statement f of x equals big O of g of x. That is inappropriate to say it. What it really means is that f of x is in big O of g of x. Or we could say that f of x is an element of big O of g of x. Since we are dealing with functions in the computer science realm, we don't usually have negatively valued functions, so it is pretty typical to drop the absolute value sign, but the definition does include it, so we will see it on occasion, and it is often appropriate to include it. All right, let's apply the definition to see if we can make a big O determination on this function. I'm given that f of x is x squared plus 2x plus 1, and I want to know, is it big O of x squared? Well, remember, we're going to pick one witness and solve for the other, so we're going to pick k equal 1. And then, since k equal 1, I'm going to make sure that x is always greater than k, but I can manipulate that to come up with two other statements that are true. If I square both sides, I get 1 is less than x squared, and if I multiply both sides by x, I get x is less than x squared, and that'll be useful for making my determination. Now I'm going to call the function in the argument of big O g of x. It's not always g of x, but I'm using it today. And here's what I mean by that. The way we're going to find c is by doing creative replacement in terms of g of x. And I'm always looking for a constant times g of x that is greater than or equal to f of x. So I'll do that term by term. Well, x squared is always less than or equal to x squared, so I can replace x squared with x squared. By k equal 1, I showed that x is always less than or equal to x squared, so I can replace this term with this term and maintain inequality. And then 1 is always less than or equal to x squared, so I can replace it here. And now I've got all of my f of x replaced with terms in g of x, and then I just add up the coefficients to get 4. And now I have f of x is less than 4 times x squared, which is 4 times g of x. That gives me my witnesses. I assumed that k equal 1, or I fixed k at 1, and then I solved that c is equal to 4 to show that f of x is big O of g of x, or f of x is big O of x squared. We'll look at a graph of it in a second, but I want to look at what if we picked x equal 2, or k equal 2. If I pick k equal 2, I can find perhaps another witness, or c. Well, if k is 2, if I multiply both sides by x, I get 2x is less than x squared. And I also have 1 is less than x squared. Why is that? If I square both sides, I get x is greater than 4, but 4 is greater than 1, so I can say that x squared is greater than 4. But 4 is greater than 1, so x squared is greater than 1. And now I'll do creative replacement. X squared is less than or equal to x squared. For k equal 2, 2x is less than or equal to x squared. And 1 is less than or equal to x squared. And if I add those coefficients up, I get 3. So if I fix k equal 2, then I can calculate that c is equal to 3. All right, next slide we'll look at f of x and g of x. Okay, so here's g of x. You can see that uh, f of x is growing faster than g of x, but at k equal 1, 4x squared will dominate it, and that illustrates that f of x is big O of x squared.